Hello everybody and welcome to my online user meeting talk on digital rock physics with GeoDict 2021. My name is Jens Oliver Schwarz and I want to give you a very quick introduction about my person. So I hold a diploma in geology and paleontology from the University of Darmstadt in Germany. I moved then finally on to get a PhD in geology as well from the University of Bern in Switzerland. Became later on the lab manager of a microcity lab at the University of Mainz and also worked there in research projects. And then 5 years ago, I joined the Math2Market GmbH as an application specialist for digital rock physics. And in the meantime, I'm also working as the team leader for business development and still working as the business manager for digital rock physics. My talk will be divided in 3 sections. First of all, I will give you a short introduction about digital rock physics in general. Then I will speak about the existing features that we have for that application in GeoDict, what we call then the greatest features we have. And then I will also give you an outlook about the new developments in GeoDict 2021 as the latest features that we developed for our software. So what is the motivation for doing digital rock physics? Actually, in the end, you want to maximize the oil and also gas production from your reservoir. And how can digital rock physics be of help in that aspect? So what you see here is a schematic sketch through a 3D oil reservoir, in which you have different rock types. For instance, you have here a cap rock, which is basically impermeable to all kinds of fluids, and you have the reservoir rock with a high porosity and also high permeability. Within this rock, you have then the oil and gas sitting. As you see here, you have a structure which actually traps oil and gas, and finally you want to produce them from that structure. To do so, you need to drill some wells and also locate the wells in the right positions and so on. Digital rock physics is helping with finding the best spots and also the best ways to get the oil or the gas out from the underground. So in order to optimize the production from the reservoirs, oil and gas companies use numerical tools as well, the so-called reservoir modeling. In these simulations, fluid flow in the reservoir is modeled on the kilometer scale. Therefore, the reservoir rock is subdivided by a regular grid and each grid cell is assigned individual rock properties. Based on this information, the overall reservoir properties are computed. The input information to the model, which are the individual rock properties, typically derive from lab experiments on samples derived from drilling operations. These experiments can take up to 1.5 years and are quite expensive. Digital rock physics digitalizes such experiments and delivers results already after 2 to 3 weeks, and so digital rock physics provide a massive increase in productivity. The general workflow for reservoir modeling requires bridging of several orders of magnitude. We are going down from the kilometer scale of the reservoir to the meter scale of a grid cell of the reservoir model to the centimeter scale of the core sample. And then finally to the micrometer and also the nanometer scale of the pore structure of the rocks. Now we know about the motivation for digital rock physics or digital rock analysis, but what is the actual workflow? The digital rock physics workflow is divided into 3 steps: sampling of the reservoir rock, imaging of the reservoir rock, and finally simulation of rock properties on the rock image, which also includes image processing. So in the next slides I will give you a short overview of our existing digital rock features in GeoDict. GeoDict has many features for digital rock physics and starts out with image processing and segmentation, where we are constantly adding new features that are presented in the talks of my colleagues in the image processing image analysis session. Geometrical characterization comprises a bunch of features including porosity, grain and pore size distributions, quality control of samples by check for representative elementary volumes, image resolution, percolation paths, solid volume fractions of different mineral phases, and orientation and shape of individual grains and pores. We have solvers for the solution of the Navier-Stokes-Brinkmann equation and compute stationary fluid flows in order to determine absolute permeability. Two-phase flow can of course also be computed, and so capillary pressure and relative permeability are part of the portfolio. Furthermore, electric properties are included as well, and so resistivity index and formation resistivity factor and other parameters of Archie's law are implemented as well. In addition to that, also mechanical properties like Young's modulus, anisotropic stiffness, damage and material failure are available in GeoDict. Last but not least, I would like to present you with some more specialized features on the next slides. Here you see a typical workflow for image processing and segmentation with GeoDict. The original CT scan of a sandstone sample is kindly provided by the OMV Exploration and Production GmbH. The gray value image is then filtered by a non-local means filter to prepare the image for global thresholding. Non-local means filters are a standard in digital rock physics because they denoise the image while maintaining sharp boundaries between grains and pores. In the segmentation you can find 4 different phases: quartz and a high-density mineral in gray and yellow, and water and oil in the pore space in blue and red. Within the pore space, very small isolated or floating grains of quartz are located. They are marked by a white circle. These quartz grains are interpreted as artifacts of the image processing and segmentation steps. These artifacts are finally removed by an island filter, and so the sample is ready for subsequent simulations. With our Python interface in GeoDict, you have a powerful tool in hand for the automation of your workflows. You can automate repetitive tasks by recording and executing GeoDict macros, perform parameter studies in an automated workflow, generate PowerPoint reports, use the entire range of Python coding, and make all these features available for your colleagues in the GeoDict menu bar. Upscaling of flow is an often requested feature, especially for the digital rock physics and carbonate rocks. Typically, carbonates have a bimodal pore size distribution, and the small pores are not resolved by micro-CT scanners. Therefore, an upscaling procedure is required to incorporate the information obtained about the small pores by nano-CT or by FIB-SEM into the simulations on the micro-CT scale. The strategy for upscaling is to define porous regions in the micro-CT scan that contain the small pores and populate these regions with permeability values. The permeability values either derive from several nano-CT or FIB-SEM scans on which fluid flow simulations have been computed. Alternatively, a digital twin is computed from a single nano-CT or FIB-SEM scan, and different representations of it in terms of porosity and permeability are created by erode and dilation operations. For each of these representations, permeability is computed and a lookup table for the porosity-permeability relationship of that sample is generated. Finally, this lookup table is used to populate the porous regions with permeability values. Subsequently, the overall fluid flow in the carbonate rock can be computed by solving the Stokes-Brinkmann equation. The later approach with GeoDict has been published by Hannah Menke from the Heriot-Watt University. Fluid flow that alters the pore space or the solid materials of the porous medium through it flows, better known as reactive transport, is quite common in the geosciences and plays also for applications in the oil and gas industry a big role. Examples are acidizing treatments in carbonate reservoirs, environmental remediation, nuclear waste storage, CO2 sequestration, formation damage, and many more. Reactive flow is a Python script built on the shoulders of AdiDict, FlowDict, and MatDict that provides the principal numerical tools for reactive flow available in GeoDict. Furthermore, specific tools, for example acidizing treatments, are readily available for direct usage, as can be seen by this video of calcite dissolution. The video shows typical dissolution structures that form under different flow regimes. Cores and core plugs used in digital rock physics workflows originally derive from elevated pressure and temperature conditions, the so-called reservoir conditions. However, micro-CT scanning is generally executed under ambient conditions. Not considering reservoir conditions may introduce significant errors in digital rock physics workflows because the reduction in pressure and the associated increase in porosity have a large impact on the computed rock properties. Applying an uniaxial compression on the micro-CT scan simulates a re-establishment of reservoir conditions and results in closure of pore throats and reduction of pore throat sizes, finally leading to a reduction in permeability. If these effects are not corrected, digital rock physics will systematically overestimate the permeability of reservoir samples. The numerical re-establishment of reservoir conditions represents a rather simple method to correct for these effects in comparison to conduct the micro-CT scans of the plugs under in situ conditions. The 3D image report is an example for the automatic PowerPoint reports that can be generated with Geodict. This specific report helps to find artifacts in your gray value data and is basically a quality control tool. The tool allows you to check a set of 2D slices, examine fly-through animations, and also includes this all-in-one in a PowerPoint presentation. So, after looking at the existing features in Geodict, we will now put the spot on the new developments in Geodict 2021. One of the most important rock properties that is sought after is relative permeability. The general workflow in Geodict to compute these parameters, for instance for oil and water, are determination of the distribution of oil and water in the pore space for different saturations of one of the phases. Choosing of saturation levels for the calculation of relative permeabilities and the input parameters for the solvers. And finally, solving the Stokes equation in the water phase, treating the oil phase as solid and vice versa, meaning solving the Stokes equation for the oil phase while treating the water phase as solid. With this method, relative permeability for quasi-static fluid distributions are computed, assuming that no interaction at the fluid-fluid boundaries take place. The determination of the distribution of the different fluid phases is done by the pore morphology method. As every method, it has its limitations, and in Geodict 2021, some of these limitations have been removed. The pore morphology method is a geometrical approach that predicts the distribution of two phases inside the pore space of porous media by pushing spheres into the structure and reducing the sphere radii for simulation of drainage. For imbibition, the algorithm pushes spheres outside the structure and increases the radii. The superposition of these spheres represents the distribution of the non-wetting phase in the pore space. By the introduction of connectivity checks in the two fluid phases, the method is also able to simulate residual phases. By the use of the sphere radii in combination with the Young-Laplace equation, the method predicts the capillary pressure. Lately, the introduction of interface radii that are larger than the pore radii enabled the pore morphology method to construct different contact angles, for instance, allows by this material-dependent contact angles. Advantages of the method are that no partial differential equations have to be solved like in other methods, and so the method has very low runtimes and memory requirements. Assumptions of the method are that the phase distributions are quasi-stationary and so no dynamic processes can be simulated, and it also assumes cylindrical pores in the porous medium. With the new quasi-dynamic pore morphology method introduced in Geodict 2021, it is possible to simulate non-monotonic pressure curves by controlling the interface displacement with a user-defined parameter, the so-called step size. What are the benefits of these improvements? In Geodict 2020, the capillary pressure increases or decreases always monotonically, and this behavior leads to large saturation jumps when small pore throats are passed, and vice versa in imbibition. In Geodict 2021, large saturation jumps have been eliminated. The addition of a user-defined step size for the fluid interface displacement leads to a quasi-dynamic fluid interface development. This can be best seen in the video. The video here shows a comparison between the pore morphology method in Geodict 2020 on the right and 2021 on the left for a primary drainage in a 2D schematic sandstone geometry. As mentioned before, large saturation jumps are eliminated in the new Geodict version, and in combination with more dynamic fluid interface developments, also the resulting fluid distribution is different. The changes in the pore morphology code go also along with changes in the graphical user interface. The old methods have not been removed from the software, and the new features can be added by the user. Activating the checkbox Use Constant Flow Rate method enables the new quasi-dynamic pore morphology method and offers sub-options for non-monotonic capillary pressure and thin wetting layers. On the later, we will have a closer look on the next slide. The before mentioned user-defined parameters for the step size for the fluid interface displacement is the interface step size. Larger values approach the old pore morphology method, and smaller values lead to more intermediate fluid distributions. In nature, water films on the nanometer scale exist on water-wet grain surfaces and may even build a percolating network. To consider these thin water films in the simulations is a challenge. The films themselves are of course not resolved in the micro-CT scans, and so they have to be modeled into the structure. In Geodict 2021, the feature Thin Wetting Layers does this job. This feature simulates thin water films by treating residual wetting phase near the moving wetting front as connected. The distance to which these water films extend is constant, but its value can be defined by the user. The video on the right gives you a visual impression of this new feature. As part of the improvements for the pore morphology method, also a new tool for the generation of gas trapping curves is provided in Geodict 2021. Gas trapping curves serve as an estimator for the producible amount of gas from a reservoir and serve also as input data for reservoir modeling. Hence, they represent an important feature for the oil and gas industry, which is now available in Geodict as an app. The graph shows gas trapping curves for different contact angles, given here as the contact angle between the solid and the wetting phase, which is water, and different initial gas saturations. All these calculations have been possible with previous Geodict versions, but now it is fully automated and more convenient for the user to use. With this, I'm coming to the end of my presentation and would like to thank you all for your attention. Thank you.